Hello everybody, welcome to the week 1 video. So we're going to continue our notes on hybridization theory, which is a theory to account for the observed molecule shapes, very much related and integrated with Vesper theory, which is valence shell electron pair repulsion. So we'll talk about 3 different sets of electron pair domains. So if we have 4 electron pair domains, these are all the notes that we took in class on Thursday. So 4 electron pair domains, we have tetrahedral electronic geometry, the s orbital, and the 3 p orbitals, so px, py, and pz, hybridize to form 4 identical sp3 orbitals. So something like carbon in the molecule methane, CH4 at the bottom here, has 4 electron pair domains. A single bond is an electron pair domain, along with a lone pair and a double bond and a triple bond. All of those are 1 electron pair domains. So the carbon and its bonds to hydrogen have tetrahedral electronic geometry, and in this case, tetrahedral molecular geometry. So we can show that using a wedge and a dash. I have an image here that's from the book. I'm going to bring this over to the side. That shows CH4 methane in 3D. So each of the sp2 orbitals are shown with this blue lobe here. I'll highlight and then I'll erase that. That's one side of the sp3 orbital, and then the small lobe is over there as well. So each of the 4 identical sp3 orbitals bond with 1 hydrogen, 1s orbital. And that creates the 4 bonds. It's in a tetrahedral shape. Another example of a molecule with 4 electron pair domains is NH3. Oops, we'll add the electrons when we do the Lewis structure. So NH3, we have nitrogen in the center. We have 3 hydrogens. So nitrogen is bonded to 3 hydrogen atoms. I'm adding in the wedge and dash already, but you might draw the Lewis structure first and then identify the geometry. But we see that there are 4 electron pair domains around nitrogen, so it also has an sp3 hybridization. We can draw the sp3 orbitals on nitrogen similar to how they're drawn in the image from the book. So nitrogen, that is sp3 hybridized, has 4 identical sp3 orbitals. So one is overlapping with 1 hydrogen, another overlaps with the other hydrogen, one overlaps with the other, and the 4th one is holding that lone pair. So these are the sp3 orbitals. Notice I'm leaving off that small other lobe because that's not the one that's involved in bonding, and usually those are left off. And then the hydrogen 1s orbital overlaps with the nitrogen sp3 orbital, and that's where we have a bond. Now, both of these have tetrahedral electronic geometry, but they have different molecular geometry. Let's create a table and then we'll talk about the difference. So we will have number of bonds, number of lone pairs, an example, molecular geometry, and let's do bond angle as well. And this is a table specifically for atoms with 4 electron pair domains. So we'll make a different table for atoms with 3 and atoms with 2. Okay, so if we have 4 electron pair domains and all of them are bonds, so we have 0 lone pairs, an example of that is methane. Its molecular geometry is the same as its electronic geometry, so it is tetrahedral. And the bond angles in a tetrahedral shape are 109.5 degrees. So that's the distance between, or the angle between 2 outer atoms. So that angle there is 109.5. Now if we have 3 bonds in 1 lone pair, an example is NH3, which we drew above. It has tetrahedral electronic geometry, but its molecular geometry is different. So molecular geometry, we're focused on placement of atoms around the central atom. And we no longer have an atom above that nitrogen the way I've drawn it there. The hydrogen atoms are all below the nitrogen, and there's 3 of the hydrogen atoms. We call this trigonal pyramid. Trigonal pyramidal. The bond angles here are 107.3 degrees, so slightly lower, smaller angle than tetrahedral molecular geometry. And that's because this lone pair up here takes up more space than if those electrons were part of a bond and repels the other electrons in bonds around it. So that causes the hydrogens to get a little bit closer together, so we have a smaller bond angle. Then lastly, if we have 2 bonds and 2 lone pairs, so total for all of these we have 4 electron pair domains. An example of this is water. So H2O, oxygen has 2 lone pairs and 2 bonds. The molecular geometry here is bent. And bond angles are even smaller, 104.5 degrees. What's helpful for bond angles, I think, is to remember 109.5 for 4 electron pair domains or tetrahedral, and then remembering that trigonal pyramid is a little lower and bent is even smaller. Now, all of these molecules or any atom that has 4 electron pair domains, all are sp3 hybridized. And have tetrahedral electronic geometry. Electronic geometry takes into account the lone pairs. Molecular geometry only takes into account the atoms that are bonded, so the bonds that are present. Okay, so this is all of our information about 4 electron pair domain molecules, or atoms with 4 electron pair domains. Let's talk about molecules with 3 electron pair domains. These molecules, so if we scroll up here, instead of having tetrahedral electronic geometry, they have trigonal planar electronic geometry. Different than trigonal pyramidal. Trigonal planar. An example here is ethene. So this molecule, the carbon here, has a double bond, which counts as 1 electron pair domain, and 2 single bonds, so a total of 3 electron pair domains. And for an atom that has 3 electron pair domains, we're listing out atomic orbitals, it will hybridize only 3 atomic orbitals. So this atom has 3 sp2 orbitals. It has 3 sp2 plus 1 unhybridized. So one of the p orbitals is unhybridized, but 2 of the p orbitals and the s orbital is hybridized. And the sp2 orbitals look very similar to sp3. This orbital is just slightly shorter or smaller than an sp3 orbital due to less p character. So fewer p orbitals are being hybridized, so that longer lobe is shorter because we have fewer p orbitals being hybridized. So ethene, this molecule, if we draw out an orbital picture, just going to redraw the structure, but only going to draw the single bonds for now, or the sigma bonds. Now each of the carbons in ethene are sp2 hybridized. So that means that this carbon, one of the sp2 orbitals, overlaps to form the carbon-to-carbon bond. One forms carbon to hydrogen, one forms carbon to hydrogen. Same thing is true, I use a slightly different blue, for the other carbon. So already, right here, we can see a carbon-to-carbon sigma bond or a single bond. Now each carbon atom also now has an unhybridized p orbital. So if we draw that in, I'll shade it to make it stand out a little more. So we have an unhybridized p orbital on this carbon, unhybridized p orbital on this carbon. Now these two orbitals overlap. We can draw that with a kind of curved line to connect them. And this is what forms the pi bond. So the overlap of unhybridized p orbitals forms a pi bond. We'll write that out here. So that represents pi bond. The direct overlap of hybridized orbitals between carbon and carbon is the sigma bond. And then let's not forget, we have 1s orbitals from hydrogen. And these are this overlap right between the two is the carbon to hydrogen sigma bond. So the green circles are carbon to hydrogen. I'm sorry, the green circles are hydrogen 1s orbitals. The dark blue lobes are the sp2 orbitals for the carbon on the left. The light blue lobes are the sp2 orbitals for the carbon on the right, and then the purple orbitals are the unhybridized p orbital. So if we now think about if we have one of the electron pair domains as a lone pair, we have slightly different molecular geometry. So let's make another table. I'm just going to make sure it's consistent with this one. So we'll have a table atoms with 3 electron pair domains. All are sp2 hybridized. And trigonal planar electronic geometry. Okay, so we'll do number of bonds, number of lone pairs, example, molecular geometry, and bond angle. Okay, so 3 electron pair domains. Let's start with if we have 3 bonds and 0 lone pairs. An example, we'll do ethylene. We're focusing on that carbon, or either carbon really. Molecular geometry is the same as electronic, trigonal planar. And bond angles, so for 3 bonds to be as far apart from each other as possible, bond angle is 120 degrees. Now let's say we have 2 bonds and 1 lone pair. Let's just say, for example, we have a carbon with a lone pair bonded to 2 hydrogens. This is a very unstable carbon because it doesn't have a closed shell. But theoretically, if we think about this molecule, this would have a bent molecular geometry, just like when we have only 2 bonds for tetrahedral electronic. And the bond angles are still 120 degrees. They're not affected by the lone pairs. Now, a lot of times when we are showing geometry in Lewis structures, this is where we'll consider, if we have an sp2 orbital, we'll draw bond angles to represent that 120 degrees. This is something you'll get used to over time. I'll give you feedback on homework to remind you of this. So for drawing, let's do CH2O. Now, I'll tell you the connectivity of this molecule. We have a hydrogen bonded to a carbon, bonded to an oxygen. That carbon is double bonded to oxygen, bonded to 2. Well, right now we're looking at a 180-degree bond angle here and a 90-degree bond angle underneath the carbon. But this carbon is sp2, it has 120-degree bond angles, so we would draw it more accurately by considering that bond angle and having the hydrogens placed like that. Or you could have, you can change the placement of the outer atoms, but keep that general bond angle here around, even at 120 degrees. All right, I will end the video there. So when we come back on Tuesday for class, we will do linear electronic geometry, so 2 electron pair domains, and then continue our notes from there.